Okay, if you don't already have them with you, this is going to be a problem with analysis of variance. Please make sure that you print and have available for you the formulas for analysis of variance, the F table, and the Q table. In the course of working each of these problems, we'll need all three of those. Okay, so this is a problem as get this set up here. Okay, so this is a Anova problem, or an Anova problem, A-N-O-V-A, which stands for analysis of variance. And we do, in fact, have in the problem variances, in this case, 3 variances. If we had more than 3 groups, we would have more. But what I want to make sure is that you do not get caught up in the name analysis of variance. This is still a test of means. So if we just had these first 2 groups, and we had sample sizes and means for the sample means and sample variances or standard deviations, we would be doing a test for the difference between 2 means. All we've done is add a third one, and so now we have really basically, are there any differences among a group of 3 population means, because we have 3 groups. The Anova is a pretty flexible procedure. In fact, you can use it for, actually you could use it for 2 groups, 3 groups, 4 groups, 5 groups, and a host of other things that are beyond the scope of this class that test things like interactions and a bunch of other things. In fact, you could take a whole semester and talk about nothing other than all the things that analysis of variance will do. So what we're going to be doing is just called the one-way Anova, which just means there are no interactions or anything. We're just looking at the differences between group means. In this case, in this problem, 3 means, but you could have 4 or 5 or whatever. In fact, for this class, except for things we work with a computer on, we certainly will not have any problems that do 4 or 5 means. It just means more arithmetic, which if we want to get to that, we'll use a computer. Well, anyway, the null hypothesis is that all 3 population means are the same. That's like our HOs that we've had before. There's no difference. In this case, not only it's not just mu A not equal to mu B, but all 3 population means are the same. The research hypothesis, HR, is that at least one of the following is true. Mu A not equal to mu B, which, by the way, if that is true, mu A is not equal to mu B, then HO is not true. But even if that were true, if we couldn't show that, we could show that mu A is not equal to mu C. That, again, by itself would invalidate HO or allow us to reject HO. And then finally, even if if we couldn't have any of those inequalities, if we could go on to say mu B is not equal to mu C, that, again, by itself would be enough to reject HO. All of those 3 could be true, or any 1 or 2 of them being true would reject HO. I hasten to add here that one, I think, good thing about analysis of variance when you're working problems on homework or an exam or anywhere else is that the hypotheses stay like this. There are no like 1 or 2 tail kind of things. These will be the hypotheses when you do a one-way analysis of variance. All right, the decision rule. With Anova, you'll be using the F table or the F distribution. The F table is where we'll get the values for the F distribution. And it's always going to be reject HO if F test is greater than some value. This is always a one-tailed upper. It's always greater than. So with the F test, you don't need to worry about less than minus or any two-tailed tests or anything. It's just reject HO if F test is greater than all the time. So if you look at the F table, you'll see that you have along the top degrees of freedom for the numerator, and along the left-hand side degrees of freedom for the denominator. We need both of those before you can look up the critical value for the F test. So first of all, K is equal to the number of groups in your analysis. In this case, we have three groups: advanced, intermediate, and beginner. The total sample size in T is just the total sample size, which in this case is 30. It's just the sum of the three group sample sizes. So for the ANOVA itself, and be careful on this because there's a degrees of freedom at the top that goes with the ANOVA, and then down at the bottom here, if you look where it says Tukey's HSD, slightly different formulas for degrees of freedom there. Actually, for the denominator, they're the same, but they differ for the numerator. So make sure you get the right ones there. The degrees of freedom for the numerator for the ANOVA test is K minus 1, or 3 minus 1 is equal to 2. And the degrees of freedom for the denominator is the total sample size minus K, which is equal to 30 minus 3 is equal to 27. And if you go on to your the F table that I've provided, and this is, as many of our tables, just part of the table, but you'll see can't get the exact number on here. You can go, if you go down to 2 degrees of freedom in the numerator and run down that column, you'll see you can get to, in the denominator, 25, and then you can get 30. Always use, how should I put it, philosophically and technically, the thing you should always do is use the larger of the two of those, or the one with the smaller degrees of freedom. So we will use the 2 and 25, or the 3.4. So we're going to reject HO when F test is greater than 3.4. I'm going to go ahead and compute MSE right now. MSE, well, let me just, before I compute MSE, what we're really going to do is we're going to now compute F test, and that's going to be mean square treatment divided by mean square error. So the treatment is sort of difference between means. How far apart are the means? So we've got sample means of 24, 27, and 30. What we're going to get is some measure index of how far apart those means are, at least on average, how far apart do they differ from one another. And the mean square error is going to be based on variance, which just tells you how variable the data are, how much sampling error. That's what standard deviation and variance measure is, the amount of sampling error that you have in a particular set of data. Well, anyway, MSE is just equal to the average of the three variances, or 21.54 plus 18.64 plus 17.76. Take all of that, divide by 3, and you should get an MSE, which is equal to 19.31. Okay, so the next thing you need to compute is the grand mean. And that's really just an intermediary value that we need to compute MSTR. So remember, down here it says compute F. We've kind of already have a start on that. F test is MS TR divided by MSE, and we just computed the MSE to be 19.31. So the grand mean, you can see it's X bar with another bar on it, the mean of the sample means. It's just what it sounds like. Take X bar A plus X bar B plus X bar C and get the average of them. That's going to be X bar bar, the mean of the sample means. And so in this case, we had sample means of 24, 27, and 30. Divide that by 3, and you're going to get 27. Now the formula for MSTR looks a little nasty, but if we break it down, it's really not nearly as bad as it seems the first time you see it. MSTR is equal to NA X bar A minus X bar bar squared. I'm going to continue that progression in a minute. That's all over K minus 1. But the sample size in group A was 10. The mean in group A was 24. The overall mean, the grand mean, X bar bar, was 27 squared. All that's going to be over 2. And then we're just going to continue that progression. And I guess I'll write this over to the side here. That first part then, 3 squared is 9 times 10 is 90. And I'll just go ahead and write that over here. So continuing up above here, we did it for group A. Now we're going to do the same thing for group B. And for group C. So for group B, the sample size was 10. And in this class, we're going to have equal sample sizes in all of the problems. I told you Anova was a large topic, and that actually does lead to some changes in the formulas and so on. But we're just going to get the basic idea of a one-way Anova. And the simplest case is when you have equal sample sizes. In fact, if you're ever doing an experiment and you have control over sample size in each group, you should, for some reasons that I probably won't get into this semester, but maybe, you should use, and you can just take my word for this one, use equal sample sizes if you can. Things work out in terms of some of the assumptions for Anova if you have equal sample sizes. Well, anyway, back to this. The sample size for group B was 10. It had a mean for group B of 27 minus 27 squared, so that's of course going to be 0. And then plus 10 in group C, sample mean 30 minus the overall mean, the grand mean of 27 squared, that's 90. And so all of that comes out to be 90. That's MSTR, and that's what's going to go here. Then you make your computation. 90 divided by 19.31 is 4.66. That is greater than 3.4. Therefore, you reject HO, and you conclude at least one of the following is true. Mu A not equal to mu B, mu A not equal to mu C, mu B not equal to mu C. So to this point, we've done what in some of the problems is just part A. We've set up the hypotheses and tested the original hypothesis that the 3 population means are all equal or there's at least one difference. The next part is which specific means differ. There's a lot of different tests that you can use for this. I'm going to show you how to use Tukey's HSD, or honestly significance difference test. We need a little bit more room for that, so I'm going to erase this stuff that's on here and scroll down a bit. Okay. So what I want to start with on this, after I get my marker set up here, what I'm going to start with is just rewriting the conclusion that we have so far, and that is that at least one of the following is true. Mu A not equal to mu B, mu A not equal to mu C, and mu B not equal to mu C. Then for each one of these, what I'm going to do is get the corresponding difference between sample means, and I'm just going to get the absolute value of that. So when I'm looking at mu A and mu B, I'm going to get the absolute value of x bar A minus x bar B. And that's equal to the absolute value of 24 minus 27. That's 3. Then for A and C, I'm going to get x bar A minus x bar C, and that is 24 minus 30, and so the difference in absolute terms between A and C is 6, and for B and C, (27) minus 30, and I've got 3. So you can take it as this difference between sample means of 3, 6, and 3. That's the information that's how big the difference is in the sample. Remember, in general, what we've done is we've said we'll take the difference in the sample of the effect and divide by some measure of sampling error to decide whether or not we have a large enough difference between sample means to declare a difference between population means or between the corresponding population means. Well, HSD is a little bit different. HSD, or honestly significant difference, what we're going to do is we're going to calculate a value. And we will compare that value directly to these numbers we just calculated. And the difference we're going to get here is going to be anything above this difference between sample means. Any sample means that are differ by this much or more indicate a corresponding difference, that there is a statistically significant difference between the corresponding population means. You might look at this as the smallest difference that yields to a significant result between population means. Well, anyway, it's equal to Q, which is a number we'll look up from, surprisingly, the Q table. That's a well-hidden kind of thing. It's equal to Q times the square root of MSE over N. I'll call that NG. It's the size of the sample that you had in each group. So it could be NA, NB, NC, any one of those. It's going to be 10 in this problem. That was the number that we had in each sample. And for Tukey's HSD test, it does require that you have equal cell sizes, at least for the formulation of it we're using. Okay, so we're going to need degrees of freedom for is just equal to k, which is 3 in this case. The degrees of freedom for, remember in Anova it was k minus 1. This is where it differs on these. It's just k when we do the Tukeys. The degrees of freedom for the denominator is still total sample size minus k, or 30 minus 3 is equal to 27. And we'll make the same kind of thing we did on the other one. We'll go down to 3, and we're between 20 and 30. Always go to the lower degrees of freedom, or the higher critical value there. The 3.58 is what I'm going to use there. You know, in a problem like this where we're not going to interpolate or anything, if you really went for the other one, I wouldn't be that upset. I'm really looking at the process here. When we get to problems, some of the other problems with fewer numbers, we'll be able to look up an exact F value or an exact Q table value. Well, anyway, then our MSE in this problem was 19.31 divided by 10, and all of that, when I calculated earlier today, that came out to be 4.97. So now I'm going to take this value. This is how far two sample means need to differ before we can conclude that the two population means that correspond to those sample means differ. That's how large it needs to be. So I'm really just going to go and I'm going to put an asterisk next to, in this case, the 1. It could be more than 1. The 1 mean where one difference that is greater than the 4.97. So what we can conclude is that there is a difference between A and C. And in this case, if you go back and look at the results, remember, we're talking about time, so lower is better. That when we use the advanced level of training, it took 24 or whatever I don't know if that was in seconds or minutes or whatever. But anyway, it took 24, let's say, seconds, as opposed to 30 seconds for beginner training, level of training. So it was faster when you used the advanced than when you used the beginner. On the other hand, you cannot say, even though they differed by 3, you can't say that there was, in the sample they differed by 3. It's not enough to say that the population means between advanced and intermediate were different, because it did not exceed this cutoff value of 4.97. The same thing for intermediate and beginner between groups B and C. We simply didn't have enough evidence to conclude that the population means differed. So we rejected HO. We included at least one of the following is true. That's what we did with the Anova before we got to the Tukey's HSD test, which is called a post-hoc test. You'll see that in some computer programs and things that you might be using. In the HSD, then, we identified which specific one or more of those were actually at the root of having at least one of those different. In this case, the only difference we could detect was between A and C, or between advanced and beginner.